Hello everyone, this is a video about irreducible elements, prime elements, and irreducibility tests in rings. So let's get started with the definitions. So let R be an integral domain. And then first of all, what is a unit? A unit in a ring R is an element such that there is an inverse in the same ring. So there's some other V in R such that U times V is equal to V times U equals 1, the one in the ring. Now, what is an irreducible element? Irreducibility and primality are two properties that very much resemble each other from the point of view of the integers. It looks like they should be the same property, and they are in some rings, but not in others, as we shall see in a moment. So if I have an irreducible element is a number that is an element of the ring that is not a unit, and every time I have a factorization of it as in the ring, as a product of two things in the ring, then one of them must be a unit. So if pi is a times b, then a is a unit or b is a unit. Now, a prime element is a number or an element of the ring that is not zero and not a unit, and such that every time the prime element divides a product, then it divides one of the two factors. So if it divides AB, then it has to divide A or it has to divide B. Now, as I said, the prototypes of these elements are in the integers, in the prime elements. The primes in the integers are usually these positive numbers, 2, 3, 5, 7, 11, 13, 17, and so on. But as a ring, -2 has the same properties of irreducibility and primality that we've just described. So all of these elements are prime and irreducible. In the Gaussian integers, in Z adjoint I, well, it turns out that 3 is prime and irreducible, but 5 is not prime and it's not irreducible, because 5 can be written as a product of two numbers, 1 plus 2i and 1 minus 2i, and neither one of those is a unit. The units in Z adjoint I are plus or minus 1 and plus or minus I. So this is a non-trivial factorization, and that implies that it's not prime and it is not irreducible. However, this factor here, 1 plus 2i, is a prime element, and 1 minus 2i is another prime element. Let's show that, in fact, every prime element in a domain is an irreducible element. Next, I'm going to show that the converse is not true in general, that an irreducible does not need to be a prime element, but prime implies irreducible. So take pi to be a prime element, a non-zero prime element, and suppose, to show that it is irreducible, suppose there is a factorization a times b with a and b in the ring. Now, clearly, pi is a times b, so pi divides a times b, and since it is prime, that implies that pi has to divide a, or pi has to divide b. Without loss of generality, let's assume that pi divides a. That means that there is to be divisible by pi in the ring R, means that there is another element C in the ring, such that A is equal pi times C. That's what it means for pi to divide A. And therefore, now if I substitute this formula for A in this formula for pi, then pi has to be equal to pi times C times B. Now, this is an integral domain, so there's a cancellation law, so I can cancel out these pi's and get that 1 is equal to C times B. But C and B are in the ring, and this is the one in the ring, so that means that B is a unit. So by assuming that that pi divides A, then by assuming that pi has a factorization AB, we've proved that one of them has to be a unit. B in this case is a unit, and if I had decided that pi divides B, then I would get that A is a unit. So in either case, pi is an irreducible element. But as I said, irreducible does not mean prime. So take R to be Z adjoint the square root of -5, one of these pure quadratic rings, then pi is equal to 2 is an irreducible element. To prove that it's irreducible, there is no possible factorization of the number 2 that does not involve a unit. then you can use norms. Use the norm in this quadratic ring to prove that 2 is irreducible. And what happens is that 2 does divide 6, of course. 6 is 2 times 3. But 6 has a different factorization, which is 1 plus the square root of minus 5 times 1 minus the square root of minus 5. And 2, you can show that, I leave this as an exercise for you, that 2 does not divide 1 plus the square root of minus 5 in this ring, and 2 does not divide 1 minus the square root of minus 5. So 2 cannot be prime. So 2 here is an example of an irreducible element that is not a prime element. Now, a very important property of irreducible elements is that when you have at least a PID, a Euclidean domain, or a PID, if you mod out by the principal ideal generated by pi, then you get a field. So R modulo pi R is a field when R is a PID and pi is an irreducible element. So let's show that that's the case, that this is a field. We're going to use this, in fact, as a criterion for irreducibility. So let A be an element of the ring, and consider the class of A in the quotient of R by pi R. We want to show that R pi R is a field, and well, it suffices to show that this is a field. Clearly, this is a domain, and we just need to show that every non-zero element is a unit. So that's what I'm going to do. Take A bar to be an element in here that is non-zero, and I'm going to show that it is a unit, so I'm going to construct a multiplicative inverse. Since A is non-zero here, that means that A is non-zero modulo pi, and I'm going to consider the ideal generated by A and pi. Now, this ring is a PID, and therefore this is generated by some element B. So this is a principal ideal generated by B. And pi is in the ideal, and therefore pi is in the ideal generated by B, and that means that pi is a multiple of B, or that B divides pi. There are two options now. Since pi is an irreducible, there's only two options. Either B is a unit, or B is itself pi times perhaps some other unit. So what happens in either case? If B is a multiple of pi times a unit, then we'll remember that A and pi generate the ideal generated by B. Then B divides A, so because B is equal to the ideal generated by A and pi, then B divides A, but B is unit times pi, so pi divides A, and that would imply that A is congruent to 0 modulo pi. So A is actually 0 in the field R modulo pi, which is a contradiction because we assume that A was a non-zero class. Therefore, this condition cannot happen, and we must have B is actually a unit. But then the ideal generated by B is the ideal generated by a unit, and the ideal generated by a unit is the entire ring. And that means that the ideal generated by A and pi is the ideal generated by 1, the entire ring. But in particular, I can write 1 as a combination of A and pi for some x and y in the ring. So 1 is ax plus pi y, and then now you can just mod out by pi. If you throw this in the quotient of R modulo pi, then what do you get? You get that 1 is congruent to A times x modulo pi, and then this x in R is a unit, is the inverse of A modulo pi, and therefore A is a unit in the quotient R modulo pi, and therefore R modulo pi is a field. Let me give you an alternative proof of this theorem. And remember that R modulo an ideal, in this case the ideal generated by pi, is a field if and only if that ideal is a maximal ideal. Notice that the ideal generated by pi cannot be the entire ring because pi is not a unit itself, because pi is an irreducible element. So it is a proper ideal, and let's show that it is a maximal ideal. Well, if suppose there is some other ideal between the ideal generated by pi and the ring R, then because we are working over a PID, this ideal I, whatever that ideal I has to be, whatever it has to be a principal ideal, let's say generated by A. So the ideal generated by pi is contained in the ideal generated by A is contained in R, and therefore this inclusion says that pi is a multiple of A, so A divides pi. But pi is an irreducible, so A must be a unit, or, well, if A is a unit, then A would be generated in the entire ring. So the ideal I is the entire ring. Or the other possibility, since pi is irreducible, is that A itself is pi times some unit. But if so, the ideal generated by pi and the ideal generated by a pi times a unit are the same, and therefore the ideal generated by pi and the ideal generated by A is the same. So if there was an ideal in between, it has to be the maximal ideal or the entire ring. So that means exactly that pi is a maximal ideal. And here's an application of that theorem we just proved. So take f to be any field and let p of x be a polynomial with coefficients in f. And suppose that polynomial is irreducible in the ring of polynomials f of x. Then the quotient is a field. That's what we just proved, that if you have an irreducible element in a ring, if you do the quotient of f of x by the ideal generated by that irreducible element, you get a field. But this allows us to construct some interesting fields. For example, x squared plus 1 is irreducible in the reals, in polynomials over the reals, and therefore the quotient by the ideal generated by x squared plus 1 is a field. And in fact, this is none other than the complex number. So this field is a model for the complex numbers. And more interestingly, in my opinion, is the following. Let p be a prime number in the integers, and let q of x be a polynomial with coefficients in fp. Fp here is, for example, you can take this to be z modulo pz. So it's the field with p elements. So you can take it to be the integers modulo p, for example. So q of x is a polynomial with coefficients in a field with p elements. And suppose that polynomial is irreducible of degree n. Then the quotient of the polynomial ring by the ideal generated by that one polynomial that is irreducible over this ring is a field. But this is a finite field. In fact, the representatives for this would be polynomials up to degree n minus 1 modulo qx with coefficients ai's in the field, which there are p possibilities. So there's p possibilities for each one of those coefficients, and all those elements are different. So this is a field with p to the n elements, which is interesting. If you have only seen before fields with p elements, now we can construct element fields with p square elements. So for example, I can construct a field with 4 elements. How? Start with a field of 2 elements, so z modulo 2, and we're going to find a field with 4 elements. Take q of x to be x squared plus x plus 1. This polynomial is irreducible over f2. Why? Because it is quadratic, so if it was reducible, then it would have to have a non-trivial factorization as a polynomial of degree 1 times a polynomial of degree 1. But polynomials of degree 1 mean there would be a root over f2, and over f2 I can check 0 squared plus 0 plus 1 is congruent to 1, and 1 squared plus 1 is 3, which is congruent to 1 modulo 2. So there are no zeros modulo 2, so this has to be irreducible over f2. And that tells me that this quotient has to be a field with 4 elements. So the representatives for the elements are polynomials a plus bx, so they are just the polynomials 0, 1, x, and 1 plus x, such that, for example, if I multiply x by 1 plus x, that's x plus x squared, which is modulo x squared plus x plus 1, the product of these is 1. So x is a unit, 1 plus x is a unit, and they are inverses of each other. So that is a field with 4 elements. By the way, note that z modulo 4 is not a field because well, the class of 2, for example, is a 0 divisor, so that is not a field. So this is an example of a field with 4 elements. And using the same construction, you can build you can build fields with p to the n elements for any prime p and any n. So now the natural question is, well, how do we determine that a polynomial is irreducible? So I can construct these fields. For example, is this polynomial irreducible in Zx? Is this polynomial irreducible? Is this polynomial irreducible in this ring? Well, we're going to develop methods to check whether these polynomials are irreducible. Note that if the degree of the polynomial q is 2 or 3, then using the degree, then we can see that if it is reducible, then q has a root. So that is one way to check irreducibility of polynomials of degree 2 and 3, especially in fields with finite number of elements, because I can check all the elements and see if they are roots. So for example, x squared plus x plus 1 is irreducible in f2x. That's what I did a moment ago, just by checking the 0 and 1 are not roots. X squared plus 1 is irreducible over the reals because we know that the roots of these are complex numbers. We know that any real number, a square plus 1, will be positive. So it cannot be 0. So there are no roots over the real number, so it must be irreducible. Are there any roots for this polynomial over q? Well, we know there is the rational root theorem that if you have a root that is a rational root of a polynomial with integer coefficients, then the numerator has to divide this coefficient and the denominator has to divide this coefficient. So that tells me that the only possibilities for roots would be within plus or minus 1. And you can test that 1 is not a root, that minus 1 is not a root, therefore is irreducible over q, and therefore is irreducible over the integers as well. Now, if the degree of the polynomial is bigger or equal to 4, then it can be reducible without having roots. So for example, this polynomial that I had before, x to the 4 plus 4, it might look irreducible at first sight because there are no roots, but it does factor as a polynomial, as a product of two polynomials of degree 2, each one of which does not have a root over the integers or over the rational numbers, but it does factor. So this is not irreducible over the integers. So how are we going to check if a polynomial is irreducible? We have several methods. The first one we're going to talk about today is the reduction modulo pi test, which is the following. Suppose R is a PID, and suppose pi is an irreducible element. Suppose you have a polynomial q, a monic polynomial q. This is we're going to work with this reduction modulo pi test for monic polynomials. So suppose q is a monic polynomial such that when I consider it in the quotient r modulo pi, remember we talked about this when it's irreducible, this is going to be a field. So when we reduce it and we work with this polynomial modulo pi in this now coefficients in a field, and suppose that that reduction is irreducible, then q itself is irreducible also over the ring. So let me show you an example of how this works. So suppose I have q, x squared plus x plus 1 in the integers, and I want to show that it is irreducible over the integers. Then I take p to be 2, which is an irreducible element over the integers, take p to be 2, and work with the quotient z modulo 2x. Then now this polynomial modulo 2, so all the coefficients have been reduced modulo 2. So this polynomial is irreducible in here because this is f2. This is z modulo 2 is a field with two elements. And I just proved before that this polynomial is irreducible here. Since it is irreducible over this quotient, then it has to be irreducible over the integers as well. So let's give a proof of the reduction modulo pi test. Let q of x be monic over the ring R, and let pi be an irreducible element for the ring R. Let q bar be the reduction in the quotient R modulo pi, and suppose that the reduction q bar is irreducible over this new ring. Then suppose that q itself has a factorization. Okay, so suppose we do have a factorization of q over R gx times h of x. And we want to show that one of those two is a unit polynomial to show that it is in fact also irreducible. So suppose g and h are polynomials over R. Now, g of x will be some polynomial, a n x to the n plus dot dot dot, and h of x will have also some expansion as a polynomial. And then when I multiply those together, what I'm going to get is, well, the leading coefficient is going to be an times bm times x to the n plus m, which has to coincide with the leading coefficient of q, which is x to the, I guess, if this is an actual product, n plus m, have to add up to the degree of q. But q is itself monic, so what I get is that an times bm is equal to 1, and therefore an and bm have to be units in my ring. And they multiply to be 1. So q, which is equal to g times h, I can divide by 1 and then replace the 1 by an times bm and distribute the an and bm. So now I look at q is equal to g divided by an times h divided by bm. And g divided by an and h divided by bm are monic polynomials. So without loss of generality, I can assume that I have a factorization of q times is equal to g times h, and everything is monic polynomials. Great. Now that I have that factorization, I'm going to pass to the quotient and reduce q in the quotient r modulo pi, and that's going to be equal to g bar times h bar. And now everything is happening in the quotient ring r modulo pi, which we know is a field now. And everything is monic here. Since everything is monic, when I reduce, the degree doesn't drop. So the degree of q and the degree of q bar is the same, and the same thing happens for g and h. All the degrees are exactly the same. But q bar itself is by assumption irreducible, and I have a factorization in here. So one of the two has to be a unit in the ring, but in fact, because this is a field, this is a polynomial ring over a field, the only units in a polynomial ring are actually the units in the field. So it has to be some non-zero element. But that means that the degrees is just a unit, so the degree of g bar is 0 or the degree of h bar is 0. And again, the degrees of g and h are the same as the degrees of h bar and g bar, so either the degree of g is 0 or the degree of h is 0. And since they are monic, then that says that g or h is 1, and therefore q is an irreducible polynomial. So for example, take the polynomial x cubed plus x plus 1 over the integers. I want to prove the irreducibility, so I can reduce modulo 2 and check there are no roots. This is a degree 3 polynomial, and I can show that it's irreducible modulo 2, and therefore is irreducible over the integers. How about x to the 6 plus x plus 1? This is degree 6, so just checking roots is not enough. But if I want to prove the irreducibility over the integers, I can check irreducibility modulo 2, because there is only very few irreducible polynomials that could divide this polynomial. If there is a non-trivial factorization, it has to have factors of degree 1, 2, or 3. So let's check those. In degree 1, there are only 2 degree 1 polynomials that are irreducible over f2, and those are x and 1 plus x. And this is not divisible by those. In degree 2, there is only one degree 2 polynomial, 1 plus x squared is the only degree 2 polynomial that is irreducible over f2, and this is not divisible. And in degree 3, there is 2 irreducible polynomials of degree 3. This is not divisible, so it has to be irreducible modulo 2, and therefore it is irreducible over the integers as well. Now, how about x cubed minus 2? Suppose I want to prove that it's irreducible over the integers. Well, let's try some primes. Reduction modulo 2 brings me to x cubed, which is reducible, so I cannot use the reduction by pi method. How about modulo 3? If I reduce modulo 3 minus 2 is congruent to 1, and x cubed plus 1 has a factorization. So this is reducible, so it is not irreducible, so I cannot use modulo 3 to prove irreducibility over the integers. How about modulo 5? It is also reducible. So I have to keep going, and then modulo 7, I can show there are no roots modulo 7, and therefore it is irreducible modulo 7. And that implies that because 7 is an irreducible element of Z, that implies that it has to be also irreducible over the integers. So you can see that sometimes you have to work a little hard and you have to try several primes to find a prime that works, the reduction modulo pi works. However, that is not always the case. There are some polynomials, for example, x to the 4 minus 10x squared plus 1 is irreducible over the integers, but it is reducible modulo p for all primes p. So the reduction modulo pi test does never work for any single prime p. And therefore, you have to prove that this is irreducible using other methods. So now we're going to see other methods that we can use for polynomials beyond this reduction modulo pi test. So a new method that we're going to use is the Eisenstein irreducibility criterion. This is how it works. Let R be, so this works for what we call Eisenstein polynomials. So let me first define what is an Eisenstein polynomial. Let R be a PID, and let pi be an irreducible element of my ring R. Take a monic polynomial Q in the ring R, then we say Q is Eisenstein at pi if pi divides every coefficient, not the one here, but every other coefficient of the polynomial. Every I is divisible by pi, but a0 is not divisible by pi squared. Then these polynomials are going to be irreducible. Polynomial that satisfies those two conditions is called Eisenstein, and those are going to be irreducible polynomials. Let's show why. So here's the theorem that if you have a PID, an irreducible element, and you have a polynomial that is Eisenstein at pi, then Q is irreducible. Why is that? Take Q to be a monic polynomial. Pi divides all the coefficients AI. Pi squared doesn't divide the constant term. And suppose we do have a factorization gx times hx in R that is non-trivial. So the degree of g and the degree of h is bigger than 0 for a contradiction. As before, like we did in the other proof, there's a trick to see that I can, without loss of generality, I can move constants around, so I can assume that q, g, and h are all monic polynomials. And since I have a factorization, I can pass to the quotient. So I can look at the factorization that is associated to that in the quotient R modulo pi and in this ring. Now, this is a field. So this is a polynomial ring over a field, and that's going to help. Because of the fact that Q is Eisenstein, pi divides every coefficient except the monic coefficient. Therefore, the reduction of Q is x to the n modulo pi. And moreover, something we're going to use that we'll prove at some other time is that if you have a PID, then you have a unique factorization domain. And since this product of G bar times H bar, by the way, this is a PID, is a field, and therefore this is a unique factorization domain. We will show that those are true things. But in any case, this is going to be factorization of x to the n as a product of two polynomials. Therefore, each one of these G bar and H bar have to be powers of x. So there is some unit, u, times x to the r that will be equal to G bar, and H bar will be some unit times x to the s, where u and v are units, and r plus s have to be equal to n, the degree of q bar. Which is equal to the degree of Q because Q was monic. So R is the degree of G bar, but because G is assumed to be monic, is also the degree of G, and S is the degree of H, which is also the degree of H bar. Then, because G bar is U times x to the R with R the degree of G bar, then pi divides all the coefficients of G except the leading coefficient. And similarly, pi divides all the coefficients of H except the leading coefficient. And therefore, what is A0, now going back to the ring R, that is Q evaluated at 0. So that is because there is a factorization of Q as G times H, that is G at 0 times H at 0. But you can see that when I evaluate at 0 G and H, I get 0 modulo pi and I get 0 modulo pi. So this divides Q0 by pi twice. So A0 will be congruent to 0 modulo pi squared. There is a factor of pi here, and there's a factor of pi there, so it's at least a factor of pi squared. But that is a contradiction because we assume that Q was Eisenstein, so A0 cannot be 0 modulo pi squared, and that's a contradiction we were looking for, and therefore Q of x must be irreducible. Great, so let's see some examples. For example, x cubed minus 2 is an Eisenstein at 2. It's an Eisenstein polynomial at 2 over the integers because 2 is an irreducible, and 2 divides every coefficient, and 2 does not divide, or 4 does not divide the constant term. Similarly, x to the n minus 2 is Eisenstein at 2, and therefore is irreducible over the integers for any n bigger or equal to 1. So this is nice because it allows me to generate irreducible polynomials of any degree. That's one of the uses of Eisenstein polynomials and Eisenstein's criterion. So this is an irreducible polynomial for any n. How about this polynomial? This polynomial is not Eisenstein at 5 because, well, 5 does divide 15, 30, and 75, but 75 is 25 times 3. So 5 squared divides 75. So I cannot use 5 to determine whether this is an irreducible polynomial. However, it is Eisenstein at 3 because 3 divides 15, 3 divides 30, 3 divides 75, but 9 does not divide 75, and therefore that tells me that this is an irreducible polynomial over the integers. How about x cubed minus 2 over z adjoint I over the Gaussian integers? Now, I can't use 2 as an irreducible for Eisenstein's criterion because 2 is not an irreducible in z adjoint I. We know that 2 factors as 1 plus I times 1 minus I. So this polynomial in here is actually x cubed minus 1 plus I and 1 minus I. So you could think like, oh, maybe I can use the criterion for 1 plus I, but 1 plus I, although it is irreducible, 1 plus I squared divides 2. That now that we have more units, that sometimes it's a little bit obscure whether that happens, but this is the case, that 1 plus I squared divides the constant term. So this polynomial is not Eisenstein at 1 plus I either. Let me show you that 1 plus I squared divides 2. By squaring 1 plus I get 2I, and therefore 2I times a unit minus I is equal to 2. So therefore 1 plus I squared, which is 2I, does divide 2. So it is not Eisenstein at 1 plus I either. So I can't use Eisenstein's criterion in this case. Now, let me just give you one last example in terms of polynomials. So polynomials in two variables, I want to prove that this polynomial is irreducible. How do I do that? What I'm going to do is consider this polynomial as a polynomial in x, such that the coefficients are in this ring z adjoint y. Now, this is a field, so this is a PID, z adjoint y, and this polynomial is now Eisenstein at pi equals y. Pi equals y is an irreducible element in this ring, and you can see that y divides every coefficient, but the constant term is not divisible by y squared, so it is irreducible. So it is Eisenstein at y, and therefore is irreducible. So it has to be irreducible as a polynomial in this polynomial ring. Okay, so that is all for today in terms of irreducibility tests, and I hope you enjoyed the program.